Welcome to Integral Calculus. Integration answers two big questions: how much accumulates and how much area sits under a curve. There are two complementary viewpoints: geometric, area under the curve; algebraic, antiderivative, when f prime of x equals f of x. An antiderivative f gives the indefinite integral as f of x plus c. A definite integral captures net area and total accumulation. We write the integral from a to b of f of x dx. Think of slicing the interval into many thin pieces, multiplying height times width, and summing. In the limit, the sum becomes the definite integral. The fundamental theorem of calculus links both views. It says the integral from a to b of f of x dx equals f of b minus f of, where f is an antiderivative of f. Let's do a quick example. Compute the integral from 0 to 2 of 3x squared dx. The antiderivative of 3x squared is x cubed. Evaluate x cubed from 0 to 2, that is 2 cubed minus 0 cubed. The result is 8. Integration also accumulates change in real life. If v of t is velocity in meters per second, then the integral from a to b of v of t dt gives displacement in meters, s of b minus s of a. Finally, remember indefinite integrals represent families of antiderivatives. You always include plus c, because any constant shifts the antiderivative but leaves its derivative unchanged. Summary: integration as area and accumulation, evaluate with antiderivatives and the fundamental theorem, and always track units and constants carefully. You are now ready to practice integration.
In this lesson, we evaluate a definite integral with a fast symmetry trick. We will synchronize each algebra step to the narration for a crystal clear flow. Step 1. Write down the integral I. I equals the integral from 0 to pi over 2 of sine to the fourth of x over sine to the fourth of x plus cosine to the fourth of x dx. We will keep this expression in view as the target. Step 2. Introduce the complementary integral j. J equals the integral from 0 to pi over 2 of cosine to the fourth of x over the same denominator, sine to the fourth of x plus cosine to the fourth of x dx. Notice the denominators in I and j are identical. We'll box them to keep that visual cue. Step 3. Use the complementary angle substitution in j. Let u equal pi over 2 minus x. Then du equals negative dx. The limits flip. When x equals 0, u equals pi over 2, and when x equals pi over 2, u equals 0. Rewriting j gives the integral from u equals pi over 2 down to u equals 0 of cosine to the fourth of open parenthesis pi over 2 minus u close parenthesis over sine to the fourth of open parenthesis pi over 2 minus u close parenthesis plus cosine to the fourth of open parenthesis pi over 2 minus u close parenthesis times negative du. Using the cofunction identities, cosine of pi over 2 minus u equals sine u, and sine of pi over 2 minus u equals cosine u. Therefore, j becomes the integral from 0 to pi over 2 of sine to the fourth of u over cosine to the fourth of u plus sine to the fourth of u du, which is exactly I. So j equals I. Step 4. Add the two integrals. I plus j equals the integral from 0 to pi over 2 of sine to the fourth of x over the common denominator plus cosine to the fourth of x over the same denominator. Combine the fractions. The numerator becomes sine to the fourth of x plus cosine to the fourth of x over the same denominator. That simplifies to 1. Therefore, the integral of 1 from 0 to pi over 2 equals pi over 2. Step 5. Use j equals I to finish. Since j equals I, we have 2, I equals pi over 2. Divide both sides by 2, I equals pi over 4. That is the exact value of the original integral. We are going to evaluate an integral by parts, iterated once, and keep the visual steps perfectly aligned. The problem is, evaluate the indefinite integral of e to the x times sine x dx. First, recall the integration by parts formula. The integral of u dv equals uv minus the integral of v du. Now, first pass. Choose u equals sine x, and dv equals e to the x dx. Then du equals cosine x dx, and v equals e to the x. Apply the formula to get the integral of e to the x sine x dx equals e to the x sine x minus the integral of e to the x cosine x dx. We still need that remaining integral. Compute the integral of e to the x cosine x dx with integration by parts again. Choose u equals cosine x and dv equals e to the x dx. Then du equals negative sine x dx and v equals e to the x. So the integral of e to the x cosine x dx equals e to the x cosine x plus the integral of e to the x sine x dx. Now, we combine both results and solve. Let capital I be the integral of e to the x sine x dx. From the first pass, we have I equals e to the x sine x minus the integral of e to the x cosine x dx. From the second pass, the integral of e to the x cosine x dx equals e to the x cosine x plus I. Substitute this into the first equation to get I equals e to the x sine x minus e to the x cosine x minus I. Move terms to solve. 2I equals e to the x times quantity sine x minus cosine x. Therefore, I equals 1/2 e to the x times quantity sine x minus cosine x plus the constant c. We are done. The integral of e to the x times sine x dx equals 1/2 e to the x times sine x minus cosine x plus the constant c. Fundamental theorem of calculus, part 2, also called the Leibniz rule. Differentiate the function f of x equals the integral from x squared to x of natural log of t dt. Assume x is positive, so that natural log of x makes sense. Step 1. Recall the Leibniz rule. If big G of x equals the integral from of x to b of x of f of t dt, then the derivative g prime of x equals f of b of x times b prime of x minus f of x times a prime of x. Now, let's identify the pieces for our problem. Step 2. Plug into the formula exactly as written. F prime of x equals natural log of x times 1 minus natural log of x squared times 2x. We will simplify this next. Focus on natural log of x squared and the 2x. Step 3. Use the logarithm identity. Natural log of x squared equals 2 times natural log of x. Substitute that into our derivative to get f prime of x equals natural log of x minus 4x times natural log of x. Step 4. Factor the common term natural log of x. F prime of x equals natural log of x times left parenthesis 1 minus 4x right parenthesis. Final answer. The derivative equals natural log of x times 1 minus 4x. Volume of revolution using the disk method. Find the volume formed by revolving the region bounded by y equals x squared, y equals 0, and x equals 2 about the x-axis. Step 1. Sketch and visualize. Draw axes and label tick marks. Plot the parabola y equals x squared. Mark the vertical boundary x equals 2. Shade the region between the curve and the x-axis from 0 to 2. When this region spins around the x-axis, it creates a bowl-shaped solid. Step 2. Set up a typical cross-section. At some x value, take a thin slice perpendicular to the x-axis. Its height is y, which equals x squared. When the slice revolves around the x-axis, it forms a solid disk. So the radius are of the disk at position x equals x squared, and the inner radius is 0. The area of that disk is pi times r squared, which becomes pi times x to the 4th. We will use this cross-sectional area in our volume integral. Step 3. Write the volume integral. We add up all of those disk areas from x equals 0 to x equals 2. So the volume equals the integral from 0 to 2 of pi times x to the 4th dx. Step 4. Compute the integral. The antiderivative of x to the 4th is x to the 5th over 5. Evaluate from 0 to 2 to get 32 over 5. Multiply by pi to get the final volume. In this lesson, we will evaluate an improper integral using a fast visual substitution cue. The goal is to evaluate the integral from 0 to infinity of x times e to the negative x squared dx. Step 1. Rewrite as a limit because the upper bound is infinity. The integral from 0 to infinity equals the limit as r goes to infinity of the integral from 0 to r of x e to the negative x squared dx. Step 2. Spot the quick visual cue. Inside the exponent we have x squared, and out front we have x dx. That is perfect for the substitution u equals x squared. So let u equal x squared. And then du equals 2x dx, which gives x dx equals 1/2 du. When x equals 0, u equals 0. When x equals r, u equals r squared. Therefore, the integral from 0 to r of x e to the negative x squared dx becomes 1/2 times the integral from 0 to r squared of e to the negative u du. Step 3. Integrate the exponential. The antiderivative of e to the negative u is negative e to the negative u. So we have 1/2 times bracket negative e to the negative u evaluated from 0 to r squared. This simplifies to 1/2 times the quantity 1 minus e to the negative r squared. Step 4. Take the limit as r goes to infinity. Because e to the negative r squared goes to 0 very fast, the limit becomes 1/2 times 1, which is 1/2. Therefore, the value of the improper integral is 1/2. Now, the quick intuition. Match x squared in the exponent with x dx in front using u equals x squared. That collapses the integral to a simple exponential with total area from 0 to infinity of 1, and the factor of 1/2 remains.
Thank you for watching. Tap like, share, and comment, and then follow and subscribe for more quick problem-solving tips. Let's make maths simple. One video at a time only on Myverse Maths.